To finish out Lesson 7, we're going to go ahead and do a couple more example problems so that you are more familiar with the different kinds of friction dynamics problems that you may encounter. This is not an exhaustive list by any means, it's just a little bit more exposure to different kinds. So we're going to look at a situation where we have a car sliding to a stop. We want to know how far do you slide before coming to a stop. So we are going to go ahead and start by identifying our knowns and unknowns. We know that our initial velocity here, and that is moving to the right, we can assume the right is positive, is our 6.8 meters per second. We know that we are going to go ahead and come to a stop. That tells us that our final velocity is then 0 meters per second. So we want to then know how far do we go before coming to a stop. In order to know how far we travel while we're having this change of speed, we do need one more piece of information, and that is the acceleration. We do need to go ahead and find that as well. And you say, well, don't we need time? Well, we could go through the whole process of finding time, to then find the change in position, to then find everything else, but we don't need it. We do have a time-independent formula. Let's go ahead and recall the fact that we have this here. So we do have this formula. We will be going ahead and solving for this change in x. When I rearrange this equation, because I'm going to go ahead and simplify some of my math, we know our final velocity is 0. We can end up seeing this. So like I said before, we need to go ahead and find the acceleration from this problem. To find the acceleration, we know that acceleration is caused by forces acting on an object. We're going to look at the forces on our car. So if we go ahead and draw our box for our car, we see all of our forces are acting from the center of that car. We have our normal force supporting the car on the concrete. We do have our weight down as a result of the earth pulling on it. And then if our car is moving to the right, that means our friction is then to the left. And this is a kinetic friction since we are sliding. So this is a level surface. We are not told anything about an incline, so we can assume a level surface. We are looking at the fact that the sum of our forces in the y direction is equal to m times acceleration in the y direction. We are seeing no y acceleration, so this term is then 0. All right. Our y terms are our normal force up being positive, our weight down, which is negative, is equal to 0. So our normal force is equal to our weight. And remember that our weight is equal to m times g. So our normal force is equal to mg in this particular case. So that's what's going on in the y direction. We now are more interested in what's going on in the x direction. You might think, well, why did we go through the whole trouble of solving for the y if we're only interested in the x? Remember, frictional forces is equal to our coefficient of friction multiplied by our normal force. We did need to find that normal force out to get the complete picture of what was going on. So, moving on to the x direction, sum of forces in the x is equal to the mass times the acceleration in the x direction. Because my car is slowing down, my acceleration is opposite the direction of my velocity. Because the acceleration is opposite the direction of my velocity, that then means if my velocity is positive, my acceleration is negative. That goes ahead and makes my left my right-hand side, negative. My left-hand side, we are looking at the fact that we only have one force acting in the x direction, and in this particular case, it is our kinetic friction. It is to the left, so this is also negative. I have negatives on both sides, so then I can actually drop them. All right, we don't forget the fact that our acceleration is going to be opposite our direction of velocity. Like we said before, frictional force is equal to our coefficient of friction times our normal force. And then our normal force was equal to our weight. Oops. At some point during this problem, you might have thought, how can I possibly solve what's going on with this car if I don't know the mass? Well, this is how. You'll notice I have mass on both sides of my equation. Because I have mass on both sides of my equation, they do actually cancel. As a result, we do find the fact that my acceleration is equal to my coefficient of friction times gravity. So we are looking at the fact that that acceleration is some portion of our gravitational acceleration. From here, we can go ahead and plug everything back into our kinematic equation we've already solved. Our delta x is equal to our negative initial velocity in the x direction squared divided by 2a, and we've now got a is equal to our coefficient of kinetic friction times gravity. And we can continue to plug and chug. Right. You might be wondering, why did I go ahead and put a negative in front of my gravity when we've dropped it from a lot of cases already? That is because we know that our acceleration does need to be opposite the direction of velocity. When I put this negative down with the 9.8, it's going to go ahead and force my delta x to be positive, right? Because if our velocity is positive, our change in distance does have to be positive as well. When we go ahead and plug everything into the calculator, do all our calculations, we do end up seeing the fact that we do take 2.95 meters to come to a complete stop at that point. Right. So that's how we're going about this particular problem. We do have another one that adds a little bit more complexity because we can't make it easy, and we're going to look at what happens when we look at something on an incline. So some college students borrow some cafeteria trays to slide down a muddy hill. They get a running start, so we have some initial speed of 4.0 meters per second. We do have a hill on a slope. And what is their speed after traveling some particular distance? So we're going to start by sketching the problem. We do have our, we do have our incline at some particular angle. We have our object on that incline. All of our forces act from that center point. We have our weight, which is straight down. We have our normal force, which is perpendicular to the surface. We know that we are moving down the hill, so then our friction is going to be opposing that motion. All right. Oops, I got a stray mark here. So for this particular problem, since our motion is down the surface of the hill, we're going to set up our axes to match accordingly. So that means, whoops, that is way too big of a pen. That means we are going to put our y-axis perpendicular to the surface of my hill, and my x-axis is going to be parallel to the surface of my hill. That means my normal force is going to be in one dimension, my frictional force will be in one dimension, and then my weight is the only one that I do need to break down into then my x and y components. Alright. Since I know that I'm going to have to break down my weight into my x and y components, I'm going to go ahead and do that now. Remember when we sketch our force of weight, we look at the fact that it can be broken into horizontal and vertical components. This component that is perpendicular to my surface is how much of my weight is in the y direction, and this part that is going to be parallel to my surface is going to be how much of my weight is in the x direction. By some definitions of geometry, this angle between my y component and my weight itself, which is the hypotenuse of my triangle, is the same angle as my incline, that theta there. When I do that, I do get the fact that Fwx is equal to Fw times sine of theta, and I also get the fact that Fwy is equal to Fw cosine of theta. Right? And then Fw is equal to mg, so this is mg sine theta and mg cosine theta. I'm not going to take this any further because, one, we don't know the masses of our objects, of our college students. We just need to know what kind of relationships we are going to have here. So now we're going to look at what's going on in the x and the y direction. We're going to start with the y, because why not? So our sum of our forces in the y direction is equal to mass times the acceleration in the y direction. We don't have any vertical acceleration the way we've set up our coordinates. As a result, we are able to go ahead and zero out that right-hand side of our equation. In the y direction, we do have our normal force, which is up, minus our y component of the weight, which is down. Right? So that does tell us that our normal force is equal to the y component of our weight, which we established was mg cosine theta. All right. Now we can go ahead and look at our x forces. So the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. We do have acceleration in the x direction, so our right-hand side is going to stay. Because our velocity is in the right direction, we're still going to have a net acceleration of positive. It's going to continue to speed up down the hill, though the friction is going to slow them down a little bit. Right? So then we have our x component of the weight, which is down the surface of the hill. So that is positive in this particular case, minus our friction, which is opposing our motion. Okay. Remember that our x component of our weight we already established is mg sine of theta, minus our friction, which is going to be mu times our normal force, is equal to our mass times our acceleration in the x direction. All right. We already established what the normal force was, so we have the mg sine theta minus mu mg cosine of theta is equal to mass times acceleration in the x direction. Look at this. We ended up with a mass term in every single part of our equation. As a result, we can go ahead and cancel all the masses out. When we do that, we get g sine theta minus mu g cosine theta is equal to acceleration in the x direction. So we've gone ahead and solved for acceleration in the x direction. We are looking for our speed after traveling a certain amount of distance. We are not given time, so we're going to use our wonderful favorite time-independent formula. Oops. So where we have this formula here, we are going to plug in for our acceleration. We already have our distance, which is that delta x here. We have an initial speed from our problem, which gives us that there. So when we go ahead and plug all those numbers in and punch it into our calculator, we do get a total velocity of 8.56 meters per second. One last bit of information is on this next slide. We are looking at what is the maximum acceleration possible for some particular car on a flat, wet road if we have some static friction. The fact that this is a flat, wet road lets us go ahead and skip a couple of steps. That goes ahead and tells us the fact that our normal force is equal to our weight, so our normal force is then equal to mg. We are not looking at anything else on this particular car. We're not looking at an additional force acting here. We would only be looking at the force of friction in the x direction, and as you know, the force of friction is equal to mu times our normal force, which is then equal to our mass of our car times the acceleration in that x direction. When we set our, we start plugging everything in, we do get mu times mg is equal to m times our acceleration. As a result, we do get the fact that our acceleration on a flat level road is going to be equal to gravity times mu. All right, this will work for any flat level surface as long as there are no additional problems present, so then you can plug and chug from there. All right, please feel free to email me if you have any additional questions.